Hello, my name is Shraddha Patel and my partner is Daniel MG. Let's start with the timeline of the history. Why is it even called the Butterfly Theorem? In a few slides, you will see a picture that is formed. The triangles make it look like the wings of a butterfly. In 1803, William Wallace posed the question in a Gentleman's Mathematical Companion. Within the first year, 3 proofs had already been published. The one that we're focusing on today was written in 1967 by Coxeter and Greitzer, 2 professors from University of Toronto and Columbia University. First, let's state it. Let M be the midpoint of a chord PQ of a circle, through which 2 other chords AB and CD are drawn. AD cuts PQ at point X, and BC cuts PQ at point Y. Prove that M is also the midpoint of X, Y. Similarity means 2 figures have the same shape but not the same size. 2 triangles are similar if all of their angles are equal. Let's take a look at triangle ABC and triangle XYZ as drawn here. If 2 pairs of angles are equal, the third pair must be equal. We will show this. Let's say we find that angle A equals angle X and angle B equals angle Y. If we look at triangle ABC, we know that the angles of a triangle have to add up to 180. This means that in order to find angle C, we would have to do 180 degrees minus angle A minus angle B. In a similar fashion, we can find angle Z by doing 180 degrees minus angle X minus angle Y. When we plug in these values, we'll get that angle C equals angle Z. Another property of similar triangles is that all of their corresponding sides are in proportion with each other. Let's prove that. Let's say we have 2 triangles ABC and XYZ. What we want to prove is this. The proportion of AB to XY is the same as the proportion of AC to XZ and BC to YZ. We will show the first part, and the last equality can be shown similarly. Our first case is assuming that AB is equal to XY. By angle side angle, triangle ABC will be congruent to triangle XYZ. Thus, AC equals XC. This is because the 2 triangles are congruent. Now, we know that AB and XY are equal, so their ratio is 1. Similarly, AC and XC are equal, so their ratio is also 1. What we wanted to show is proven. Now, let's take the case where AB is not equal to XY. I have a lemma written down here. The proof of this lemma can be found in a link posted in the description box. Let's draw a segment AU on AB such that AU is equal to XY. Next, let's draw UV such that UV is parallel to BC. From that, we know that angle AUV will be equal to angle B, their corresponding angles. Angle B is equal to angle Y because these 2 triangles are similar. Thus, angle AUV equals angle Y. Similarly, we can show that angle AVU equals angle C, which equals angle Z. AU equals XY. So, by side angle angle, triangle AUV is congruent to triangle XYZ. Thus, AV equals XZ. Now, this lemma can be found in Geometry for College Students by I. Martin Isaacs. What it says is, let U and V be points on sides AB and AC of triangle ABC. Then, UV is parallel to BC if and only if AU to AB equals AV to AC. So, we know that UV is parallel to BC, so we can use this statement. From looking at our triangle, we can see that the proportion of AU to AB is equal to the proportion of AV to AC. Since AU equals XY and AV equals XC, this equality becomes XY to AB equals XC to AC. This is what we wanted to prove. The sides of two similar triangles are in proportion with each other. Now, let's move on to talking about inscribed angles. We're going to show that an inscribed angle is half in degrees of its subtended arc. An inscribed angle A looks like this. Let AC be the diameter, and let BD be a line connecting B to the center of the circle. Then there's an isosceles triangle ABD because AD equals BD. This is because AD and BD are both radii. Because ABD is an isosceles triangle, we know that angle A must equal angle B. Also, since ADC is a straight line, we know that angle ADB plus angle BDC is going to equal 180 degrees. This gives us that angle ADB is equal to 180 degrees minus angle BDC. Accounting for all of the angles in triangle ABD, we get this equation. Angle B plus angle A plus angle ADB equals 180 degrees. Angle B plus angle A can be rewritten as angle A plus angle A. This is because angle B is equal to angle A. Angle ADB can be written as 180 minus angle BDC. This all still equals 180 degrees. We can rewrite the two A's as just 2 times angle A and keep the rest the same. Now we can subtract the 180 from both sides. This gives us 2 angle A minus angle BDC equals 0. From this, we can add the angle BDC onto both sides and we get 2 angle A equals angle BDC. If we divide by 2 on both sides, we get this equation. Angle A equals 1/2 of angle BDC. If we look at the first bullet point, we can see that the measure of an arc is given by its central angle. In our case, angle BDC is the central angle of arc BC. So, this is equivalent to saying angle A is equal to 1/2 of arc BC, which is its subtended arc. Let's extend this a little bit further. Say we have two inscribed angles in a circle, angle A and angle B. They both subtend the arc CD. Since both of the angles A and B are half in degrees of arc CD, they have to be equal to each other. Now let's get down to proving the actual butterfly theorem. We will start by drawing a line segment from points X and Y to their opposite sides. These lines form right angles to their bases. We're going to name these points R, S, T, and U. As we can see, the vertical angles RMX and YMT are equal. Similarly, vertical angles UMY and SMX are equal. Now let's look at triangle MRX and triangle MTY. We can see that they both have a right angle in common and a pair of vertical angles. This means that the two triangles are similar, as we had proven before, which gives us our first similarity. Next, we can show that triangle MUY and triangle MSX are also similar. This is because they also share a right angle and vertical angle in common. Now we're going to use what we just learned. Angle C and angle A both subtend the arc BD. This means that they are equal. We also see that there are right angles at CUY and ARX. This means triangle CUY and triangle ARX are similar. Next, we see that angle B and angle D also subtend the same arc, AC. We also see that there are right angles at angle YTB and XSD. This means that triangle BTY is similar to triangle DSX. Lastly, let's go over the proportions that these similarities bring for us. The first similarity we showed was that triangle MRX is similar to triangle MTY. This gives us the proportion MX to MY is proportionate to XR to YT. In a similar fashion, for triangles MSX and triangle MYU, we see that MX to my is equal to sx to yu. We also get these two other sets of proportions that we will use later in the proof to show more. I will now hand it off to my partner Daniel to finish off the proof.
We want to show that mx equals my, or that mx divided by my equals 1. From our triangle similarities, mx divided by my equals xr divided by yt, and mx divided by my equals sx divided by yu. Multiplying these together gives us mx divided by my squared equals xr times sx divided by yt times uy. Switching the denominators gives us the right side of the ratios we obtained from the other pairs of triangle similarities. If we substitute xr divided by uy for ax divided by cy, and sx divided by yt for dx divided by by, we get mx squared divided by my squared equals ax times dx divided by cy times by. Before we continue our proof, we need to prove the intersecting chords theorem, which states that if two chords, AC and DB, intersect at a point P inside a circle, then AP times CP equals BP times DP. To prove this, we use the fact that when two inscribed angles subtend the same arc, they are equal, to show that angle ABD equals angle ACD, and angle BAC equals angle BDC. Then we have triangle ABP is similar to triangle DCP because they have two sets of congruent angles, so the ratios of their sides AP divided by DP equals BP divided by PC. Multiplying both sides of this equation by DP and by CP gives us AP. If we want to use the intersecting chords theorem to help advance our proof, we must first determine which chords would be helpful. In our equation, we have mx squared divided by my squared equals dx times ax divided by by times cy. We want to use the chord AD with the point of intersection being x and the second chord being PQ, because then by the intersecting chords theorem, ax times dx equals px times qx. Then we want to use the chord CB with the point of intersection at y, and then the other chord is PQ. So C. Then we substitute out the products we got from the intersecting chords theorem to get mx squared divided by my squared equals px times qx divided by py times qy. If we substitute px for mp plus mx, qx for mp minus mx, py for mp minus my, and qy for mp plus my, we get an equation in terms of mx, my, and mp only, which is mx squared divided by my squared equals the quantity mp minus mx times the quantity mp plus mx divided by the quantity mp plus my times the quantity mp minus my. Distributing the right side using difference of squares yields mp squared minus mx squared divided by mp squared minus my squared. Cross-multiplying yields mx squared times mp squared minus mx squared times my squared equals my squared times mp squared minus mx squared times my squared. Subtracting out the mx times my terms and then factoring out mp squared yields mx squared equals my squared. So then mx equals my, which completes our proof.